If you want to use Lewis structures, then describing a molecule that has resonance involves drawing multiple different resonance Lewis structures for that molecule. And we've said before that the real structure of the molecule is going to be some average of those individual Lewis structures. Hybrid orbital theory gives us a way of representing that average structure. So we're going to consider two different structures for the C6H6 molecule, benzene. Both of the structures that are drawn on the screen represent good Lewis structures for benzene. All of the atoms have satisfied octets, the formal charges are all minimized, all of the rules are followed. And the only difference between these two examples is the fact that the double bonds are in a different position in the two different structures. And we can also draw a similar structure with a circle in the middle representing the quote-unquote true structure, where the double bonds are actually not localized to any two different carbons, but they're spread out across the entire molecule. Because each of the carbons in benzene has 3 electron domains, that is, it has 3 different bonds and 0 lone pairs, each carbon is sp2 hybridized, which means each carbon is going to have 3 sp2 hybrid orbitals and 1 unhybridized p orbital left over. Remember that the arrangement these orbitals will take has the 3 sp2 hybrid orbitals arranged in a plane separated by 120 degrees around the carbon atom, and the unhybridized p orbital will be arranged perpendicular to the hybrid orbitals, so perpendicular to the plane of those 3 hybrid orbitals. What that means for the central carbon atoms in benzene is that each of the sp2 hybrid orbitals on the carbon atoms will be involved in a sigma bond. 2 of the sp2 hybrid orbitals will be involved in overlapping with the hybrid orbitals on adjacent carbon atoms, and 1 of the sp2 hybrid orbitals will be involved with overlapping to the hydrogen's s orbital. And these overlaps will create the network of single bonds that extends around the entire benzene molecule. The result is that benzene will be bonded with all the carbons and hydrogens in a single plane. The unhybridized p orbitals will exist perpendicular to the plane of that molecule. Each carbon atom will have an unhybridized p orbital that is aligned with the p orbitals of the adjacent carbon atoms. And that situation means that your nearby p orbitals are aligned such that they can form pi bonds. So each carbon atom could form a pi bond with any of the carbon atoms next to it. And the way the orbitals are oriented suggests that none of those overlaps are any more likely to happen than any other overlap. And in fact, the electron density from one of those unhybridized p orbitals extends on both sides of the carbon atom. It extends towards the carbon on the left, and it extends towards the carbon on the right. And in practice, what that means is you have a pi bond that forms and extends around the entire ring. So rather than having 3 pi bonds that are localized between carbon atoms, like you can see in the images on the left-hand side of the arrow, what actually happens is that all of those p orbitals are overlapping with one another in a continuous ring around the molecule, like shown in the image on the right-hand side of the arrow. The electrons that are in those orbitals aren't localized to bonds between 2 carbon atoms. They're said to be delocalized around the entire ring system.